Now, if you've ever had to sit in front of a router and manually enter a whole slew of static and summary routes directly into a router's routing table, you know there are way more interesting ways to spend your time. Enter the world of dynamic routing protocols. The very job of these things, the reason they exist, is to relieve you of that administrative duty, to do the heavy lifting, and allow themselves a communication protocol that lets them talk amongst themselves and establish the best, most cost-efficient routes within them from one path to another. Now in this video, what I want to do is start off by talking about some basic dynamic routing concepts, okay? And first thing we're going to do is we're going to divide these dynamic routing protocols into three categories. The first one we're going to call distance vector protocols. They operate in a very specific way. There's another type of protocol that we call link state, and those operate a little bit differently. And finally, there's a third we call path vector. So I'm going to give you an overview of all three of those. However, in our studies, we need to focus on the first two, distance vector and link state. We refer to these as our interior gateway protocols. And we're going to dive in a little bit deeper on those, show you exactly how these work, so you have a fundamental difference of how these things are actually creating this topology that they need to allow our packets to go from one place to another in the most seamless way possible. So let's take a little bit of an overview here at these protocols as a whole. So what you see here is a bit of a table, very handy table here. What you see is I've got dynamic routing protocols, and I've broken them down into two particular types. The first type we call interior gateway protocols, IGPs. Okay, think of this. You could think of this as inside a LAN if you wanted to, but it's not really. We're talking about router to router to router communication. So these are WAN links characteristically. However, they typically fall inside what we refer to as something called an autonomous system, or at least some area or boundary that's within your control as a network administrator. You have multiple routers in your zone of influence, and you want them to communicate as effectively as possible, where you're going to use an interior gateway protocol for that. On the other hand, we have what we call the EGPs, the exterior gateway protocols, the things that allow our traffic to traverse autonomous system to autonomous system to autonomous system, essentially inside the internet. And there's a certain protocol that works best for that, or at least is most commonly used, and we call that a path vector routing protocol. So splitting them into two, we have our interior and we have our exterior, and then we can split them again. Our interior breaks into two types: distance vector and link state. They're very different. They accomplish essentially the same task. Each one has different administrative costs and administrative overhead, and they operate a little bit differently. And we're going to focus on understanding the key differences there. But as you can see further down the chart, distance vector breaks into two of the more common ones. We've got RIP V1 and V2, which you've worked with previously, and we have EIGRP. Okay, now RIP V2 has a cousin called RIP-NG, Next Generation, which handles and supports IPv6. EIGRP supports IPv6 natively, so we don't have a special thing there. Link state breaks into two other key protocols, OSPF and IS or ISIS, intermediate system to intermediate system. Both of these are what we call link state protocols, and they operate very, very differently. So your first task is to be able to break these things up into their classification, because once you figure out the classification, you can then figure out how they think. So this is a really important chart, and again, breaking them into two: IGP versus EGP, distance vector inside IGP versus link state, and then inside both of these we have our different types of protocols in there. Our EGP, the only one we're going to really focus on, is this path vector routing protocol called Border Gateway Protocol, BGP, and we won't be having to do much in terms of configuration, but we want to know how that works. So let's talk about how these things work in terms of differences, and what I want to do is start off by talking about distance vector. So let's look at a simple topology here. We have a topology that is under our sphere of influence, okay? All of these routers are yours. As a network administrator, we control them. And what that means is that we're responsible for configuring them, and we know how these things are connected. And as you can see in my diagram here, I've got some numbers here to represent what I'm going to refer to as the administrative distance, the cost, right? And we know that the lower the cost, the better the route, the faster or more reliable or whatever have you. It's a better route for our traffic. And so if I were sitting here with, maybe I'm sitting here at R5 and I need to get traffic to R1. Okay. Now I have multiple paths. I can see based on our network that I can traverse R2. I can also go through R4. I can also take this middle road here and go through R4 to R3 and over to R1. Now, academically, looking at it, we see the whole topology. That makes us, as administrators, we're link state people. We can see the entire picture. However, as a distance vector protocol, I cannot. What that means is that R5 can only see, if I'm running a distance vector protocol, R5 can only see and hear about information that is provided from its what we call our neighbor adjacencies. Okay, so R5 has two neighbors here, R2 and R4. Now, if R5 wants to get to R1, unfortunately, if I'm running a distance vector protocol, I don't have a picture of the whole topology. The only thing R5 knows is that I'm connected to R2 and R4, and both of them tell me that I can get there. I can get to R1 through them. Both of them tell me. Now, I have to figure out which one I choose, though, and I'm going to use some kind of administrative distance. I have to trust them based on what they tell me. Now, if I'm using RIP, right, you probably remember that RIP uses a very specific metric called hops or hop counts. Okay, it simply counts the number of routers that it has to go through to get from point A to point B. So if I'm using RIP, and I'm talking about a distance vector protocol here, R5 is going to ask R2, hey, how far are you away from R1? And R2 is going to go, well, I'm connected to it. So I'm effectively one hop for you to get here, to get to R1. R4 is going to say, hey, I'm also connected to R1. So I am also one hop to get there. Now, R4 also knows that there's a path here through R3, and it could tell R5 about this. It could say, I could get to it through R3 as well, but that would account for two hops. You got to go through two routers. And so R5 is simply going, well, I want the least number of hops possible. With RIP, that's all it's taking into account. It doesn't factor in the fact that if you add up these costs to go from here to here, it's 30. To go from here to here, it's 30. To go from here to here to here, it's actually only 25. So based on the quality or the cost of these links, this internal path is actually the smartest route for R5 from a cost perspective. But RIP, using this particular protocol right here, R5 has no way of knowing anything beyond that. It's simply looking at that information that it's getting about hops. Now, so what that means, though, is in distance vector, and what I really want you to take away is not how RIP works, but how distance vector protocols work. R5 is only talking to these two neighbors. That's it. That's where it's learning information from. And it can only share information. And R4 and R2 can only say, hey, I know the distance. I know how far it is. I can't tell you how I'm doing it. I won't give you any details of the entire map, but I can tell you how far away I am. And you can choose based on the road signs which one you choose. So think of it if you were driving to, say, I don't know, Edmonton from Kelowna. There's more than one way to get there. You can go through Calgary and then go north, or you can head up north through Jasper and go east. But there's two ways to get there. A distance vector says, go to Golden and make a choice. But I don't know what's after Golden. Just go to Golden. And then when you get to Golden, you'll have another way to go. And then when you get to Golden, you get to Calgary, and Calgary will tell you which way to go. It won't tell you how you get there, but it'll say you are X distance from Edmonton, and it'll do that. So the key thing with distance vector protocols is that this router here has no idea about the entire topology. It doesn't have any clue how many routers are beyond its partners or its neighbors. It doesn't know how many routers here. Now, you could say, well, it knows the hops, so it does theoretically know. Well, it doesn't think about how many routers. It's talking about the administrative distance. And so it's looking at that and it's deciding. But distance vector, I do not know the entire topology. I simply know how to get to the first most sensible router that's going to theoretically give me the quickest route there. Now, we have this other protocol here called EIGRP. It's what we refer to as an advanced distance routing protocol. Okay, it still works the same way as RIP in the sense that R5 has no idea what's beyond its neighbors. It really doesn't. It simply knows, however, that there's a more sophisticated way to calculate a route over hop count. So it's smarter than RIP in the sense that it can actually take into account these administrative distances. So remember, with RIP, this process would fail. It would probably throw me either through R2 to R1 or through R4 to R1. And I wouldn't be taking the smartest distance. I'd be taking the smartest distance according to RIP, but it wouldn't be the smartest distance according to my administrative cost. Well, EIGRP says, you know what, I can do better. And it uses a series of these things called K values that actually lets me figure out the cost based on this advertisement. So what R4 is going to do, so R5 says I have to get to R1. And R2 is going to say, well, this is how far you are away from me, and this is the cost I am from R1. I'm not going to tell you how many routers it is, but I will tell you how much it costs me to get there. It costs me 20 to get there. Now, over here, R4 is going to tell R5, yeah, I can get to R1 as well. I have two routes. I have one route that costs me 20, and I have one route that costs me 10 plus 5 is 15. So what I'm going to do is I'm going to tell my friend R5 that I can get there in 15. From R4. And now R5 goes, okay, well, if I take my distance from me to you and I add your distance, I now have a total picture of how much it's going to cost me to get there. I still don't know the details. They're still fuzzy beyond R4. Again, it's distance. It's a distance vector protocol, which means that R5 doesn't know the whole picture. But what it does know is that it knows that this is probably a smarter path because the information that neighbor adjacency is telling him. So EIGRP, this advanced distance vector protocol, is only sharing information from its neighbor adjacencies, but it's smarter and can calculate administrative distances a bit more practically than RIP can. So both of those work. Now, I'm giving you an overview of how these things talk at the high level here, but again, the big takeaway here is distance vector. I know only my neighbors. That's it. I don't know what's beyond. Now, the cool thing over here is I do have an alternative. I have this thing called a link state routing protocol. And the one that we're going to study is OSPF. Now, open shortest path first. And what this does, the key difference between distance vector and link state is that while distance vector only connects me with a neighbor and I can do what my neighbor tells me, once all of these routers talk, okay, once all of these guys form what's called neighbor adjacencies, what R4 will do is it will tell R5 about every neighbor that it has. And it's going to learn all the neighbors from R3. And R2 is going to share all the neighbors that it knows. And eventually, through a series of what we call link state advertisements, R5 is going to be able to map out a picture of the entire topology because it's sharing that information from neighbor to neighbor to neighbor. So the key difference here in the link state protocol is that R5 has the entire picture. So it can see the map from Calgary or from Kelowna to Edmonton, and it can go, okay, it goes Golden, Calgary, north to Edmonton. It goes Williams Lake, Jasper. I can go through this way if I want to. It has the entire map, and then it can make its own decision based on all of this information on what route it wants to use. So again, the big difference is that in a linked state, every single router has a complete picture, and we call this the topology table. All those entries are listed in there, and it has this complete picture of the overall network. And so this makes it superior to distance vector because it has this picture of everything. And if something changes, that entire topology gets updated. Now, does it cost more to converge? Absolutely. We're sharing way more information in between these routers. So it's a little bit less efficient in its convergence process, but it's so much smarter in our administration because once it has this picture, it can make smarter decisions than distance vector. So again, distance vector, I know the neighbors. Link state, I know the entire picture. And that helps me actually establish my best route. Now, in this case, in this example, EIGRP would arrive very likely at the same decision that OSPF made that says, you know what, my best route through to R1 is via R3. And OSPF is using a different metric here. We'll go through that when we get to OSPF, but they will both arrive at the same thing. So in a fairly simple environment, which one's better? Well, that's up to you, right? There's an administrative overhead with both, and you have to consider the ease of configuration. You have to configure the network traffic that both have, and but the more routers you have, the more likely you want to be working with some kind of link state protocol, and OSPF is kind of the flavor out there that you'll run into the most. So you now see the difference between the two. What is this one over here, this path vector? Well, okay, let's remember, this is exterior now. So if I were to consider this one large sphere of influence, or my area of control, or my boundary, I'm going to refer to this as my autonomous system, my AS. Everything inside here is my system. I control it. Now, I'm going to use an IGP to figure out all the ins and outs and connections in between here. But what happens outside? Okay, so think about why we use this exterior gateway protocol. Well, if we were to take Troy sitting here at his computer, right? I'm connected to a router, and then I'm connected somehow to the cloud. Now, inside this cloud, there's a whole bunch of different ISPs, there's a whole bunch of different companies, there's a whole bunch of paths for me to get this traffic through. And somewhere over here, there's another router that you are connected to that you are watching this video on. But what's going on in between? Well, I could have hundreds and hundreds and hundreds and hundreds of these things we call autonomous systems. And all of those are most commonly controlled by ISPs. So TELUS, Shaw, Verizon, Sprint, all of these huge providers and ISPs will have some kind of autonomous system. Larger companies as well, like Amazon or Microsoft or Google, they'll have their own AS as well because they're administering massive numbers of routers inside there. Well, BGP is the responsible protocol to let me decide how to get from system to system to system to system to system to get out here. Inside each system, I'm using one of these guys, but the way we share information between ASs is via this thing called BGP, this exterior gateway protocol. Now, I mentioned in the beginning of the video, it's kind of a blend of both. Okay, and in that sense, it is. What it's trying to do is provide an overall topology for every AS to know how to get through. But the problem with that, is that think of the size of the table. The topology table would be massive. Inside each of these ASs, there could be thousands of routers, and so these things are often broken down into mini areas, etc., just to control how big this topology is, right? How much information has to go from router to router to router. Well, this is a path vector routing protocol is a blend of both, but what it's really leaning closer to is a distance vector protocol, because the way it's going to work is essentially this. I'm going to have a router. Sorry, I erased my diagram, but I have a router that's heading to an autonomous system. Okay, well, I need to pass that information to another autonomous system inside my big cloud here, of course, right? I need to pass this along. I don't want to send the entire topology. right? I don't want to send the entire thing like OSPF does. What I do want to send, though, is the cost and the details of that cost through to a very specific router or representative of each AS. So we're getting into these things what we call border area routers, which basically these are the routers inside each system that actually talk to each other and share the topology. So the topology is shared. However, it's not done the same way that we do with Link State, where the routers inside here don't end up getting an entire topology. But they do get a detailed list of the costs associated with every single path. And so that's how EGPs are working. Again, not really in our studies. The takeaways that I really want you to have here is just a general feel for the differences between these guys. Okay, and so that's basically where we can end this. And if you're comfortable with what I've told you, you are in good shape to move on and dig deeper into these protocols. Remember that we have distance vector, link state, and path vector protocols. Those are the consequences of dividing our distance vector protocols into two key areas, interior and exterior. Interior, we break down and divide between distance vector and link state. We can accomplish the same things with both of them. However, each has strengths and weaknesses. RIP, that hop count thing really makes it senseless to work in any more complicated environment. But there are advanced distance vector protocols like EIGRP. If we want to do that link state, we have OSPF and we have IS-IS. And the key difference here, though, between a distance vector and a link state. Distance vector, the router only knows that it's connected to neighbors, it knows its neighbor adjacencies, and it learns information about the distances to the locations, the faraway locations, but it does not know the entire topology. And so what that means is that I'm just talking to my neighbors, that's it. In a link state protocol, as the router, as I start talking to my neighbors, I am going to end up learning everything that every neighbor knows. Not just what my neighbor knows, but all the information that their neighbors know and the information that their neighbors know. And that's going to give me an entire picture of the entire topology. And so if you understand those two differences, we'll see how that implements and affects our design as we start digging in. But that is a good foundation for understanding dynamic routing. Okay, so hopefully that helped. And we're going to move now into some of these interior gateway protocols, starting with EIGRP. Talk to you soon.